This image is a guy at MIT, presumably named Bill, who is dropping a ball, and he's dropping it against this background, which is marked every half meter. Moreover, there's a strobe lamp over here which is flashing at a rate of 1/16 of a second. And that's why you're seeing multiple images of the same ball. This is one ball being dropped once. What happens is that if the strobe is off, it's dark and the camera doesn't pick anything up. When the strobe flashes, it picks up wherever the ball is at that point. And so what you're seeing here is not multiple balls, it's the same ball, but it's just an image of that ball every 16th of a second or so. So, in the first 16th of a second, it's fallen to here, not a very long distance. In the last 16th of a second, it's fallen from here to here. It's the same amount of time, but this distance is much larger than it was up here. Now, this is not surprising at all. You know that when you drop something, the longer it's been falling, the faster it goes. And that's all that's going on here. So what I did was I measured the position of the ball at each flash and created this table. And so the left-hand column here is the time of each flash after the first one. The right-hand column is the distance that the image of the ball was from the start at each flash. Then I plotted it over here. So for example, at this flash, which was, someplace around 0.06 seconds, okay, because this axis is seconds, the ball had fallen a total distance of, 0.05 meters or so, because this vertical axis is meters. It's the meters that the ball has fallen in this many seconds from when it was dropped. This point over here is saying that after 0.41 seconds or something like that, the ball had fallen a total of about 1.1 meters. So that's what this plot is. Now, I'm going to add a trend line to this thing so that we can see what the path of the ball was while it was falling, not just these points that we measured. Okay, I've got the chart editor up, and I'm aiming it at the total distance curve, which is this blue curve here. And what I'm going to do is I'm going to add a trend line to it. I always saw trend lines in one of the earlier lessons, so here we go. Now, the problem with this trend line is it's lousy. This is a straight line, and the data clearly is some kind of curve. So that's a really lousy fit. We can do better. One of the things that you can do is you can change the type of the trend line from linear, that is a straight line which we have now, to other shapes. And what I'm going to pick as a shape is a polynomial. What a polynomial is a function which has multiple components which are in terms of things like x, x squared, x cubed, and so on. The other thing that I did was that I used the equation of the trend line that the software fit to it as the label, and that's what this is up here. All right, so let's see what that amounts to. Okay. Here we have it. Y equals 1.53 e to the minus 03 plus 0.435x plus 4.94x squared. Just one comment about this number here. 1.53 e to the minus 03 is the same thing as scientific notation, where the first part of this is expressing the significant part of the number, and the second part of it, that is the e to the minus 03, is expressing really where the decimal point is. So in scientific notation, it would be 1.53 times 10 to the minus 3. And normal notation, it will be written as 0.00153. Because 10 to the minus 3 is 0.001, and 0.001 times 1.53 is 0.00153. So that's all that is. Now, what I'm going to do is, first of all, move this thing over here so that we can see what's going on. And I set up some formula cells here to work with this table. These cells are the x values. Now the x values, remember, here are time. So what I'm going to do is I'm going to be putting in time values here. What these values are over here are the distance the ball has fallen at that time. Now, what I did here was I used this equation, okay, to create the formula for that cell. So these cells have this formula in them, and so they're calculating the y value, which is the distance the ball has fallen, when I put in an x value, which is the time that it's been falling. And the x values for this come in. There's an x value and an x squared value, but that's all in this formula. For the top one, the x value, which is used in the formula, comes from this cell. For the bottom one, it comes from this cell. Okay, so let's put one in here. All right, so what I'm going to do is I'm going to put in 0.1, which is 0.1 seconds, which is 0.1 seconds after the ball has been dropped. Now, what happens is that this is calculating the y value here, which is the distance the ball has fallen. But what I'm trying to do here is I'm trying to find the slope at this point, okay? Before we did it by making an approximation, just drawing a line in it. But what I'm going to do here is I'm going to make it more accurate by actually defining 2 points on here, getting a line between them, and then getting the slope of that line. So to do that, I have this difference here. So if I put in a difference of 0.1 seconds, what happens is, sure enough, I get 2 points. Now, what I'm going to do with those 2 points is I'm going to add a trend line to them. So here's the line that I added. Okay, it's just a linear trend line. And over here, what's happened is that the slope of this line has been calculated by the spreadsheet. What we're trying to do here is make this line tangent to the curve, but it's not here. And the reason is that these 2 points are too far apart. So what I'm going to do is I'm going to make them very close together. So I'm going to change the difference to 0.00001. Okay, it was a very small difference. But it can still calculate a slope. I mean, this looks like it's a single point. It's not. There, you can see over here there are actually 2 points in x, therefore 2 calculated points in x, and this is the slope that you get for the line between these 2 points, that is this line here. And because the 2 points are so close together here, that's a very good approximation of the slope at this point on the curve. Okay, I'm going to now do another one. These green boxes are exactly the same as the red boxes, but it's just so that I can have a different set of data. All right, so I'm going to put one up at 0.4 seconds. Okay, now this line has a much steeper slope than this line, and you can see it in the calculated slope. The slope of the red line is 1.423. Okay, the slope of the green line is 4.387. So what does this mean? Remember, slope is the vertical change divided by the horizontal change. Here, the vertical change is in meters. The horizontal change is in seconds. So what we have here, the units of the slope of this line are meters per second. That's a velocity. Whenever you have distance divided by time, that's exactly the definition of velocity. So when I get a slope at any point on this line, what I'm doing is I'm calculating the velocity of the ball at that moment in time. The velocity at the green point at 0.4 seconds was 4.387 meters per second. The velocity at this point at 1/10 of a second was 1.432 meters per second. But this is exactly what you would expect. The longer the ball falls, because it's accelerating, the faster it's going. And that's what these slopes are telling you. And you notice that as you watch this curve go up, the slope keeps increasing. That's the velocity increasing due to the acceleration of gravity.